Thevenin theorem is a very important theorem in circuit analysis. So let's look at this illustration circuit here. Suppose I have two terminals here, terminal A and B, and on the left-hand side of the terminal, I have a very complicated circuit there. And then I have a load. This load, let's just assume is a resistor. Suppose this is a load. Suppose if this load is changing, and then I want to look at the current flow through this terminal. I want to look at the current flow through this terminal. And then every time when the load is changing, then I need to analyze the whole circuit again, which involve with very complicated circuits inside this portion. We have better ways to handle this situation is to apply the Thevenin theorem. The Thevenin theorem said that this portion of the circuit, this portion, no matter how they're connected, the structure is, it can be transferred to equivalent to a voltage source in series of a resistor. So in that case, the whole circuit here, this complicated circuit can be replaced by just two elements here. Now, if I have load here, the load here is changing, and every time it's changing and the load is changing, it doesn't matter. It's very easy for me to calculate this circuit now because I already figured out what is the left part here instead of doing the whole circuit, the whole network here, the whole network, analyzing the whole network. I only need to analyze this simpler circuit here. This is one of the important applications of Thevenin theorem. Thevenin theorem, the voltage VTH is the open circuit voltage at the terminal A and B there. And RTH, that's the equivalent resistance with the independent sources are all turned off. This is a rule how we obtain the VTH and RTH. VTH, that's the open circuit voltage, and RTH, that's the equivalent resistance with all the independent sources are turned off. Now let's look at a circuit without dependent sources. For this type of circuit without any dependent source, it's relatively easy. So to obtain the RTH, the equivalent resistance, we want to turn off all the independent sources. I mean, independent current source or independent voltage source, we want to turn it off. And then we just use the simplification of the connections. And then we can figure out the resistance there. Let's illustrate the concept, use this example. Here, the terminal is A and B. Very importantly, that when we apply Thevenin theorem, first of all, we need to specify the terminal. So which two terminals are we using, are we applying the Thevenin theorem? In this case, this is a terminal A and B. We want to obtain the Thevenin theorem for this portion of circuit. So eventually, we're going to have something like this. This is A, this is a B. We're going to obtain RTH and VTH. To obtain RTH, we need to turn off all the independent sources here. There is one voltage source. We want to turn it off. How do we turn it off? We want the voltage goes to 0, so short circuit. And there is a current source here. We want to turn it off. How we want to turn it off? We want the current goes to 0, so we want open circuit here. After this treatment, let's look at the circuit. Remember, this is a terminal, this is a terminal. Okay, so this is an open circuit, and this is short circuit here. So therefore, there's a short circuit here, and this branch just disappeared. We have 3 resistors connect in this way. Currently, RTH is the resistor looking from terminal N and B to the left. In this case here, we can see 4 ohm is parallel to 12 ohm. So I draw a circuit here, 4 ohm parallel 12. I call it R0 here. That's the value of 4 ohm parallel 12. That equals to actually 4 multiplied by 12 and divided by 4 plus 12. Then this 1 ohm here, this is 1 ohm still here. That's, I call it R1. So what is RTH? RTH, that equals to R0 plus R1. This is RTH. We obtained one element for the Thevenin theorem. Next step, we found VTH. VTH is the open terminal voltage. First of all, the terminal is open. So there's open circuit here, and then we mark the VTH this way. This is a positive, and this is a negative. It has to mark this way. You cannot mark the other way around. So this is a Thevenin theorem here. Now we need to find VTH given this circuit here. So we can use a source transformation, nodal analysis, mesh analysis. So anything we learn can be applied here. One thing that confusing a lot of us is that this is open circuit, so there is no current flow through this resistor. No current here. So therefore, VTH is the same voltage from this terminal to this terminal. That's the same thing. This is VTH as well. That's regarding with this terminal. That's the same thing. So the circuit really becomes this in the purple box here now. Once we realize that VTH, that's the voltage here or the voltage here, the problem is solved. We want to solve VTH. How we obtain VTH? There are several ways. Any way is good as long as we're comfortable with. So first of all, let's look at nodal analysis to obtain VTH. For this circuit, there's only one node here. So this is the reference node here. We're going to apply KCL on this node here. And then we mark IA, IB, IC this way. Current flow in, that will be IA plus IB. Current flow out of this node, that will be IC. So what is IA? IA will be 32 minus VTH divided by 4, Ohm's law. And remember, this is open circuit here. This is open circuit. This is open circuit. This is just one branch here connected to here. So don't even consider here. And sometimes we're confused by this connection here, but because it's open terminal, there's no current flow through here. So current IB equals to 2. IC, that equals VTH divided by 12. And this is only one equation we can obtain VTH. VTH equals 30 volts here. The other way to obtain the VTH is to use source transformation. Remember source transformation, we need to recognize is there any voltage source in series of resistor, or is there any current source in parallel resistor? So in this case, we found a voltage source in series of resistor. So we're going to apply source transformation. When apply source transformation, we need to be very, very clear about the terminal. So this is the terminal, okay? Then these two elements here in series can be converted into a current source in parallel the same resistor. So this dotted line will be here. I know there's a blue dotted line here. That's different than this. So this is a source transformation here. Let me mark here. This portion here become this portion. This point, that's this point, and this point, that's this point. So nothing changed. 12 ohm still here. there is a 2 amp current source here. That's here. Our goal is to find voltage. Still, we need to recognize, so this is a VTH. So this is a VTH. So we need to find voltage here. This is our VTH. And here, this doesn't do anything. Here doesn't do anything here. From here, we combine these two current sources here. They flow into the same direction. So that will be 8 plus 2. That will be here. There is 2 resistors here, 4 parallel to 12. 4 parallel to 12, that's equals to 3. And then remember, we want to find the voltage here. That's our voltage. Nothing has been changed. So this 1 ohm here, this is our 1 ohm. This is an open circuit here. It does not do anything. So this is open circuit. So actually there's only one current flow into this resistor. The voltage will be 10 multiplied by 3. That will be 30 volts. That's the same result we obtained using nodal analysis. Now the Thevenin theorem. Thevenin equivalent circuit, we obtained 30 volt and 4 ohm.